Hello everybody. In this video we're going to look at how we can calculate the sum of the square deviation scores, or the SS value, from a frequency table. Now in front of us we have the formula for SS. SS actually has two different formulas. Both of them use the same numbers, but they approach it in a different way. On the left we have the definitional formula. The definitional formula is an easier formula, but one that requires additional steps when dealing with larger data sets. The larger your data set, the more steps you have to take. And as a result, this is useful for smaller data sets, but quite infuriating to use for larger data sets. On the right, we have the computational formula. The computational formula retains the exact same number of steps no matter how large your data set. And as a result, we're going to use that to simplify the process, because in this example, we're going to have a data set of 50. Now here on the left, we have our column of raw scores. These raw scores represent the responses our participants gave. These are the exact same ones we had in the previous video in which we measured central tendency. So let's introduce our columns, and then afterwards we'll work through them. In the C column is our scores, or X values. This represents the possible range of responses our participants could have given us. The D column is our frequency. This is the rate by which each of these responses actually occurred within our data set. The E column is the product of X times F. By taking the sum of this score, we could get the total sum of X, which represents the sum of all of these values combined. Now in F, we have an additional column, which is the product of X squared to F. This is basically the same as if we were to square the X values and then take the sum of that. The reason why we have that particular column is because the computational model requires us to treat X values a little bit differently. Notice in the formula on the left, we have sum, represented by sigma here, of X squared. This is when we would square the X values and then take the sum of those squared X values. On the right, what we have is the squared sum of X values. Here we will take the sum of X, and then after we have calculated the sum, then we will square it to produce this value. Now they're very similar. They even use the exact same wording, just slightly rearranged in order. But it's important to treat these two numbers very differently because they result in drastically different values. We'll see those in a second as we approach them. Now let us take the sum of the values we need for the next step. I am not going to take the sum of our scores here because these are not actual values. Instead, those are the possible ranges of values. I will, however, take the sum of our frequencies. The sum of the frequencies will be our n value. N is going to be necessary because it's about 1/3 of the formula itself here. The sum we get is 50 because when we take the frequency of all of our scores and add them together, that's how many times we had scores. In other words, 50. Here, the sum of x is going to represent the total value of all the x's put together. And here what we're going to do is take the sum of x squared. The sum of x squared is necessary because it's another component of the formula. This value here, 877, the sum of x squared, represents the value that would go in this portion of the formula. This value, 189, is the value that would go within the parentheses here, meaning we still have to square it. So let's go ahead and do that. We're going to take the squared sum of x, and we're going to take the sum of x squared. They are very similar sounding names, and I apologize for that, but this is ultimately what we have. The squared sum of x is going to be this value, 189 squared. So here we will take this particular number, 189, and we will use the product formula within Excel to multiply it to itself, effectively squaring it. The sum of x squared, on the other hand, 877, we already have, so we're not going to recalculate that. We'll just carry that over here. So now that we have the squared sum of x, this value here, we need to divide it by n, which is 50. So we'll go ahead and actually enter that in as 35,721 divided by 50. That gives us a value of 714.42. Now what we need to do is take the difference of the sum of x squared and that particular value. In other words, 877 minus 714.42. That will actually result in our SS value. So let's go ahead and do that. And we get a value of 162.58. Now using this SS value, we can derive standard deviation and variance. Depending on if we're dealing with the population data or the sample data, we will divide that value by a different amount. Let us assume right now that we're dealing with the data set for the population. Our variance in that case is simply going to be our SS, which is 162.58, divided by n, which is 50. Our standard deviation is going to be the square root of variance. giving us a value of 1.8. Now, if we were dealing with the sample and not the population, we would actually use a very similar formula. We would still take the SS, which is 162.58, but now, instead of dividing it by 50, we would divide it by 50 minus 1. We would do the same thing to our standard deviation, which is the square root of variance, but for the sample, and we would get these two values here. Now I'm going to set this up so we remove the extraneous decimal values we have, and it's simply 2 points past the decimal, giving us 3.32 for variance and 1.82 for standard deviation. Now notice that the sample standard deviation and variance is actually larger than the population standard deviation and variance. The reason for that is because we are reducing the number by which we are dividing the numerator by. By taking n and subtracting 1 first, we are purposely setting it up so our values are larger. The reason we do that is to adjust for the fact that we are more likely to make what's known as a sampling error in the inference we draw from our sample to our population. Long story short, when you're dealing with the sample, it's n minus 1. When you're dealing with the population, it's just straight n. Having done that, we've seen how we can use the computational formula for squared sum of deviations to then derive standard deviation and variance for either the population or the sample. Hopefully these have been informative and helpful to you, and if as need be, we'll include more videos in the future.